Swayam Prabha. Digital India. Educated India.
Yeah. So on the face of it, it looks like a larger matching could be more popular because it matches more number of people, and all the people who get matched in the larger matching but not in the stable matching would vote for it. But as it turns out, the stable matching also gets as many votes just because of its stability. So let me, okay, so let's say, so suppose M is a stable matching and N is a larger or any other matching, let's say. It may be larger, it may not be, but okay. So let's look at two people here. Okay, so the blue edges represent M and let's say the yellow edges represent N. Maybe I will draw one more. Yes. So now let's assume that we are asking people to vote. So if we look at A and B prime, can they both vote for N? Correct. So no, because otherwise they block M and M is stable. Right? So whenever we ask people to vote for M versus N, for every edge that is present in N, at least one of the endpoints is going to vote against it. So for every edge in N, at least one endpoint votes against N. That is in favor of M. But then how does N gets more votes? For every possible vote that it gets, it is also losing another vote. So if you look at all the pairs in N, at least one of them is going to vote against N. Right? So even if it is larger and endpoints like B double prime here and A prime here can vote for N, N cannot get more votes. So for every pair AI BI which is present in N, either AI or BI is going to vote against it. Possibly both will vote against N and then N will get even less number of votes, but at least one of them is certainly going to vote against N, and hence N cannot get more votes than a stable matching. So what we have concluded here is stable matchings are popular. Okay, so at least popular matchings have the nice property that if we try to find them, we are not losing out on stable matchings. They are still in consideration, and if they happens to be the largest one, we can still have them. Right? So if you look at the set of popular matchings, then they also contain the set of stable matchings. Because every stable matching is popular, and there could be unstable matchings which are also popular, like what happened in our previous example. Okay, so now the question is, okay, stable matchings are popular, and hence we are also able to find some popular matching because we know how to find a stable matching. How do we find possibly larger popular matchings if they are indeed there? So if the preference lists are complete, stable matchings match everybody, so we can't expect that there will be a larger popular matching. But if that is indeed not the case, as is there in most practical applications, then how do we find the larger popular matchings? Sorry, say, could you say it again? Yeah, so you are talking about this example that we had, right? So let me go to that example. Yeah, so this example. Yes. Only thing is it is not very immediately clear why it will be popular. Here indeed it turns out to be popular. But but your idea is that look at whoever is remaining unmatched in the stable matching and then try to match them first. Yes. So let me formalize this in terms of the algorithm. So this is a small example and only A2 is remaining unmatched from the men's side. So we can try to match A2 first. But when there are many unmatched people and we don't want to completely lose track of their preferences, so what we will do is we will give we will first find a stable matching, and then whoever is unmatched we will give them a higher priority. So let's just take this example once again. Okay. So first we find a stable matching, which is A1 B1. and now A2 is unmatched. So we want to give a higher priority to A2. So how do we formalize this? So how are we going to use the higher priority? So what we will say is that every woman here, that is all the bees, should prefer a man with higher priority over a man with lower priority. Okay? Otherwise, there will be no use of higher priority. And make every woman prefer a man with higher priority over one with normal priority. Yes. Yeah, so yeah, reservation is one such where you sort of reserve some seats and give them higher priority as compared to someone else. So here the central authority doesn't really ask the women to do that. This can be internal to the algorithm. Right? So just ask the men and women to submit their usual preferences and execute the Gale-Shapley algorithm or the modified algorithm in this fashion. So let's just execute this algorithm and see what happens. So this higher priority I will denote by star. So when A2 gets higher priority, I will denote it as A2 star. It's like a star status. Okay. So let's execute the Gale-Shapley algorithm first. So A1 proposes to B1, B1 accepts, and A2 proposes to B1 and B1 now rejects. So this we end up with this stable matching. Now we give higher priority to A2. So A2 now becomes A2 star. Okay, and now as A2 star again starts proposing. So A2 star proposes to B1. Now what should B1 do? A1 has normal priority, A2 star has of course higher priority. So B1 should prefer this A2 star over A1. So this is a modified Gale-Shapley algorithm which incorporates this star status. So B1 will reject A1 and accept A2 star's proposal. Say it again. Yeah, so we are saying that whoever remains unmatched at the end of the usual Gale-Shapley algorithm, we will give them a higher status or higher priority. So in this fashion A2 remained unmatched, so A2 now has higher priority, which I am denoting by star. So once the man gets higher priority, what can the man do? Again start proposing. So that is what now A2 star does. He proposes to B1. Okay, and what we want, we also should make women accept the people with star status, otherwise the higher priority won't make sense. So if B1 again makes the usual comparison, B1 will again reject A2 star. So the higher priority will not give us an advantage. So we say that a woman prefers a man with higher priority over a man with normal priority. So now between A1 and A2 star, B1 is supposed to prefer A2 star. Okay, so A2 star gets matched to B1, A1 gets rejected. Now what should A1 do? Yes, so A1, right now we will not give a higher priority to A1 because A1's list is not exhausted. A1 still has B2 in the list whom he can propose with normal priority. So just with normal priority, A1 goes and proposes to B2 and B2 accepts. Right? So we have a larger matching here which happens to be popular, and we have the higher priorities have actually succeeded us in giving a larger matching. Yes. Yes. So when we respected people's preferences completely and we said that there should be no pair, no man-woman pair who prefer each other over their matched partners, we landed up with stable matchings, right? So socially they seem to be the most acceptable in terms of each, respect to each individual, right? But then the drawback is that we are leaving many people unmatched. And when it comes to doctors and hospitals, you can't give that much respect to doctors' preferences compared to the patient's interests, right? The hospitals have to run. So in that sense, you are justified in slightly disrespecting individual preferences and matching more, say, doctors to hospitals, and hence running more hospitals in a reasonable way. So yes, so there is now less preference to each individual's, no, less respect to each individual's preference, but then it is in the interest of the society. Yes. Yeah, so now we have introduced some blocking pairs, which indeed means that some are matched against their wishes. But then, yeah, that is in the interest of increasing the size. Yes. Yes, so I have not given the proof at all. I will just write the formal algorithm. I may outline the proof a bit, but I'm not sure if we can spend time in the whole proof. You were saying something. Yes. Yes, but when the central authority gives that matching, they can see that there are blocking pairs and their preferred hospital also prefers them, but they are matched somewhere else. So these blocking pairs will be visible once the central authority outputs a matching, but the central authority can still say that, okay, majority of you still prefer this matching over any other matching. Okay, so that popularity part I have not proved. I will give some idea or some sketch of that proof. So let me quickly write down a simple description of this algorithm. M proposes next woman on his list. Let's say this woman is W. Actually, I should say A because that is the notation we are using. Okay, so here there is usual Gale-Shapley acceptance. So I will not write down all of it. That is, if B prefers A over her current partner, she will reject that current partner and accept A, otherwise she will reject A. So this is the Gale-Shapley part. And if A exhausted his list without star status, then A star is put in the queue of free men. And while executing this algorithm, we will again follow this principle or this rule. So we are not completely disregarding the preferences while comparing two men of normal priority or two men of higher priority. Women will again consult their own preference list. So here it's little bit of forcing that is coming because they have to accept a man with higher priority. Yes. Yeah, so exhausted his list means he got rejected from everyone. So even after giving, yes. Yes, so even if B2 is given star status, B2 is not proposing. So there is no question of accepting or rejecting B2. So if we are executing the women proposing algorithm, we will give star status to unmatched women. So the use of giving star status to A2 was that he got accepted by B1. Right? So it is natural that the proposing side is given a star status so that they get some higher priority over other men. Yes, but then how do we a priori detect that B2 is going to get unmatched? Right? So this is, no, so I did not know. So this algorithm does not say that give star status a priori. Here we are only giving star status only when A is exhausted, A has exhausted his list without star status. So exhausted list means he is rejected by everybody. So when he is rejected by everybody, we again put him in the market with star status. Whereas if we wanted to give star status to women and put them at higher preference, then like we did not know a priori whom to give it. Yes. Yes. So can you please repeat the preference list? A1 and A2? Okay. Okay, this is a good point. So now the example is like this. So the stable matching is A1, B1. Yeah. Or I will not even write the stable matching. Let's just start executing this algorithm on this example and see what happens. So someone will propose first. So let's say A1 proposes to B1. B1 will accept. Now when A2 proposes to B1, B1 will not accept. So A2 will be given a star status because now A2's list is over. And now when A2 proposes to B1, B1 now accepts. Now A1's list is exhausted. A1 can't go further. So now A1 gets the star status. And now A1 proposes to B1. So now what will B1 do? Yes. Yes. So between two men who have normal status or between two men who have star status, the usual preferences are used. So here B1 prefers A1 over A2. Sorry, here So B1 is going to prefer A1 star over A2 star. So B1 will again reject A2 star and accept A1 star's proposal. So we have ended up with the same matching here. It is no surprise because this is also the largest matching here. So it may so happen that this whole exercise of higher priority won't give us anything better. And in some cases we are indeed getting better. Yes. So now the running time will be 2 times m, which is again order of m. And in fact you can show that if you give like an even higher priority like double star, triple star and so on, then you don't retain popularity. So it is crucial that you give a higher priority only once. Yes. So if you give double star, yeah, I mean if you give more stars and more higher priorities, you may get a larger and different matching, but then that matching may not be popular. No, then you should also have a termination condition that once the matching doesn't change, you will just stop. Hmm. No, but even before doing that, at this stage you should figure out that the matching that we had at this stage, where nobody had a star, and the matching when everybody finished with 1 star, they are the same, and then you should stop. So you won't give higher stars indefinitely, but even if you give them more number of times, you will not retain popularity. So it is not very easy to see. Again, order doesn't matter, just like the Gale-Shapley algorithm. Yeah, so I really don't think I can give the proof sketch. So I can't give the proof sketch, but I will leave one small question as exercise. And can there be a smaller matching? When I say smaller, in comparison with a stable matching, which is popular. Okay. So we have shown that stable matchings are popular. We also said that there could be larger popular matchings, and we saw this in this example. Can there be smaller popular matchings as well? So if not, then just try to prove it, and that will be a nice exercise. Okay, so we will stop here, and now after lunch Meghna will resume and she will take the next 2 lectures.